Our speaker today is Deanne Hargrave. Deanne works as the Geoscience Manager for Atlantic Shore Offshore Winds, a joint venture between EDF Renewables and Shell Renewables Energy Solutions. Deanne is a recognized expert in marine shallow hazards and offshore development surveys with more than 25-year experience, leading teams, planning, executing, and delivering large complex geoscience projects. She's an active member in the geoscience community, currently a panel member of the NOAA Hydrographic Service Review Panel and several Society of Underwater Technology working groups. As an early adopter of new technology, she brings technical insights to these working groups as to the offshore wind industry. I hope you all guys enjoy her presentation. Dan, all yours.
Thank you so much. As Daniel so graciously introduced me, I'm Deanne Hargrave. Deanne, I'm the Geoscience Manager for Atlantic Shores. I work with some amazing people doing geoscience. What is geoscience, you ask? Well, that's a great question, and I could probably give you 20 or 30 different answers to that question. Today, we'll endeavor to talk about geoscience, particularly as it relates to the offshore wind industry that's picking up a lot of speed off of the east coast of the US, as well as other places around the world. So we can skip over this, that's who I am. I actually wanted to start off with playing just a quick video that introduces my team at Atlantic Shores, what we do and how that integrates into offshore wind. The reason I'd like to do that is in 6 minutes, it's a 6-minute video. It captures more than I could do probably in 30 minutes because it's been really thought through and structured. Also, it will kind of set the groundwork for everything else that I'm going to talk about today and kind of get your mind thinking about what is this geoscience, how does geoscience fit into an offshore wind project into the industry? But some of the specific questions that we're going to dig a little bit deeper into tie into things that I talked to a lot of you about earlier today. Certainly, what tools do we use? Talking with the JEPCO folks, obviously multi-beam bathymetry is right at the heart of a lot of this work. What kind of data are created? Why do we do it in the first place? How is this information then integrated into an offshore wind project? And yeah, we'll look at bringing that all together here. So let's jump into it. So I guess I'll go through a few slides here. I have maybe 10 slides. They're pretty high level and really, reserve probably 20 minutes at least to have Q&A. I think that's where we have the most fun is having the conversation, but also do feel free to pop questions in as we go along and we can tackle on the spot. So I wanted to intro with, I know that a lot of folks here are also very interested in oceanography, mid-ocean conditions, things like that. Those are a little bit outside of my wheelhouse, but I just want to say that for offshore wind, it's one of the most important things because the wind is the resource. So we have to understand it, we have to measure it, model it, and understand, if you're talking about a wind project, you have a lease area. In order to understand what your resource is, ultimately you want to know how much yield, like how much energy can we get from that resource to the homes that are going to be the end consumers. So one of the very first things for any offshore wind project is to do some in situ measurements. And one of the super cool things about the east coast of the US is most developers are sharing all the information that we're gathering. Atlantic Shores is one example. We have mid-ocean LiDAR buoys floating in our lease areas. And I just noticed a puppy in the back. And that data is being fed real time to Maracus. If you're familiar with the Maracus, I forget what it stands for, but it's the Northeast coastal ocean. Andy, help me out.
Mid-Atlantic.
Mid-Atlantic Regional something, where you can access all kinds of data about that region of the ocean. So some very cool stuff that's going on in that space. Digging more into where I come in as the geoscience manager for a project, I have a team that's built up of, as you heard in that video, geophysical folks, marine archaeologists, geologists, very heavy on the geotechnical engineering side. I'm a civil engineer and I specialize in geotechnical engineering, so at least I know what dirt is, but I'm not, I'm not into the details of geotechnical engineering, but it is a huge component of offshore wind projects. And we'll get into that here more. So, those two different kind of data sets, geophysical, you can cover a very large area with kind of a lower resolution data, but you have to interpret it. And there are a number of variables that go into that interpretation. There's a bunch of unknowns. And so geophysical interpretation is that. It's interpretation, it's a science. You're never going to get it exactly right. Geotechnical comes in, and geotechnical is where you collect the samples that are in a specific location, and you prove out the theory that you've established with your geophysical data. How do we collect that information? Usually those are on two different vessels, two very different kinds of vessels that have different people, different skill sets, different equipment. Pictured in the upper right is a geophysical survey vessel. You can see on the back a number of apparatus for towing equipment. Some of the equipment is towed behind the vessel. Some of the equipment is hull mounted. The geotechnical drill ship, pictured in the lower right, that's kind of a standard offshore drill rig used for collecting soil samples. So the cores, they're about 4 or 5 inches in diameter. These systems are dynamically positioned, so they don't need to be anchored to the seafloor to hold their position to do the work that they do. There's a moon pool that goes through the vessel. That top drive drill rig system is able to do a number of things. It can collect samples directly, bring them up to the surface, and then you take those samples into the lab and do a number of analyses on them. Or you can push in situ tools like a CPT to measure the strength of the soil where it lies. There's a lot of people behind the scenes to make all these operations go, both on the vessels, but also onshore. So we talked about already, and you're all very familiar with bathymetry data, so don't need to spend too much time here talking about multi-beams, because I'm by far the least knowledgeable person in the room when it comes to that, other than to say the tool, we use it to obviously map the bathymetry. Maybe the unique thing in the offshore wind is that the resolution of the data that we acquire, most of our projects are in, say, 40 meters or less of water. So we're using hull-mounted systems operating in the 400 kilohertz range. The resultant data sets are in the quarter meter range. And because of reasons other than getting full coverage of bathymetry, mostly driven by marine archaeology and other purposes, the line spacing actually gives us like 300% coverage or 400% coverage. So we're painting the seafloor quite well as we go along. We of course want to know what the surface is, so we do pretty standard side scan sonar surveys. with at least a 600 kilohertz system, generally towed, sometimes in tandem with a magnetometer or a transverse gradiometer, sometimes on its own. Again, these are collected on 30-meter line spacing in 30-meter water depth, so we're getting a lot of overlap. Really important data for understanding the surface where offshore wind structures are going to be constructed. So we have foundations that go into the ground. We have cables that connect those foundations. So this is really valuable information for both of those parts of the project. Of course, we want to identify any historic shipwrecks so that we can avoid those with any activities that we do. There's some really interesting things going on. When you look at projects that are being constructed in 30 meters of water, well, that was at the last glacial max, the sea level was further out, and so these areas were exposed. If you can picture it, this image in the lower middle is maybe what the seafloor or what the topography looked like prior to all the sedimentation, all the thousands of years of sedimentation, and as the sea level rose. So there are these historic channels, paleo channels, that have now been infilled, and they've been very important to know where those are as you're looking at building foundations for turbines. There are different foundation types, but most of them would penetrate through multiple layers of soil below the mudline. So it's important to know the characteristics of those soils. We measure that with not only some high resolution, ultra high resolution seismic sources, so using a spark or sound source with towed hydrophones, as well as using an Innomar sub-bottom profiler. The combination of those tools is intended to get both the deeper, lower resolution information for foundations, as well as the shallower, higher resolution information for cables. So a little bit deeper look into the geotechnical samples. Some of the tests that we do are to answer questions about the soil structure interaction, but there's a lot of other things going on. In this case, in the lower left, lower right, when you install a monopile, so this is a standard monopile. It's maybe a 9-meter diameter tube of steel that's 4 inches thick, driven, say, 30 meters into the ground. Sorry, 30 feet into the ground. These are huge things, right? So they're difficult to install, and it's super critical to know what the soil characteristics are as you're installing these for understanding, what kind of a tool do you need? How big does it need to be? What kind of installation vessel do you need? How long is that going to take? What kind of weather conditions can you do this work in? But also after it's been installed, understanding the full environment in which this thing is going to reside for the life of the engineering life of the structure. You deal with things like seabed mobility, so kind of the global seabed mobility. So sand waves. If you've done your bathymetry survey, you have mapped that you have sand waves. You can see them at that particular point in time, but you know that there's a lot of things, a dynamic environment. So those sand waves are moving. Most likely, it's something that needs to be studied and understood so that you can design a structure that will withstand all the changing environments over the 30 years or 40 years of the lifetime of the project. So we've talked about the geophysical and the geotechnical work. So large area survey, getting a good acoustic model of your entire project area. Then we've come back and we've done point data with geotechnical information. We do multiple iterations of that. Start with a kind of a reconnaissance level geophysical survey, build a ground model, decide where are you going to invest your initial money on geotechnical properties, come back, put that all into the model. We go through probably 3 full iterations of that until we've achieved the level of understanding of this cube of stuff where we're going to install our project. And we have to meet a number of milestones, including meeting all the code requirements, meeting regulatory requirements. These projects get certified by a CVA, a certification verification agent. And so it's not enough just to address design concerns and really address the the risk profile for a developer, but there are a lot of external criteria that also have to be met. This ground model is front and center to that, and the ground model can answer all of your questions about wind turbine generator foundations. Offshore substations, they have a different kind of foundation typically. Your inter-array cables, so the cables that tie the turbines together into a network offshore, and the export cables that connect that entire project from the offshore to the onshore. So when does this work happen in an offshore wind project? Well, job security for all of us, it happens throughout the entire lifetime. Fantastic thing. I would say that it is definitely front loaded though, because as you are going through the assess phase of a project, so opportunity screening, you're looking at how big are the turbines going to be? How much energy do we think we can produce out of this postage stamp of seabed? What kind of foundation type are we going to use? As you're narrowing in on all of those questions, you need to have some level of information, yet until you've made a design, until you've picked the location of your foundations, and you know what foundation type you're going to use, it's very difficult to get the actual design information you need to do the final design for that structure. So herein comes the iterative process. So it's typical to start with desktop studies, of course. Reuse, map once, use many times, right? Use all the information that's out there that we can, leverage that. And then, strategically and smartly design your efforts as you go along in parallel with the development of the design of your project. This conceptual design and basic design phase, so going from assess through select and partway through define, takes about 3 years. Like if everything goes well, it takes about 3 years. And that also lines up with the first permit that you need to even start construction. I'm talking about NEPA just a minute ago, so it all comes full circle. I'll talk about that on the next slide. So this is a big undertaking, and this is just one project, right? Where I sit, we have a portfolio of projects, so we have 3 lease areas, we have 5 projects up to 6 gigawatts of potential. All of those projects are working through these phases at the same time, but their timelines are staggered. And so we sitting here in the geoscience team get to try to puzzle all that together and anticipate what information do we need at what time to answer what question for either the engineering needs or the permitting needs. So it's a fascinating place to be. I think we have by far the most fun job of anybody in the team. And if you think about it, where we do our survey work and the data that we collect, it drives what that eventual project design is going to be. And so, of course we get it right, but if we don't get it right, then, well, you know who to blame as well. Just to go a little bit further down to the right on the timeline. Okay, so we've talked about the front end a lot of coming up with the design, parameters that go into design. Then you get into the construction phase. There's lots of monitoring and making sure that, you know, the assumptions that you've made along the way actually pan out and are true to the environment as you're doing the construction. After construction, you go into operations phase. That goes on for the life of the project, 20 to 30 years. You need to ensure that the cables are still buried, and that you don't have any other issues along the way. So there's a lot of geophysical monitoring that goes on. One thing that I didn't really talk about too much, I kind of skipped over, is all the environmental surveys that we do at the same time. So if you think about, I mean, you all know getting vessels into the field is expensive. And so once you have them there, you want to optimize them, do as many things from a single platform as you possibly can. One of the really nice pairings is doing geophysical work with environmental baseline. So a key component to an offshore wind project is understanding the essential fish habitat. A lot of the tools that you use to map essential fish habitat are the geophysical tools coupled with geotechnical. So you take that same information and you kind of repurpose it with that other goal in mind. You can achieve both of those at the same time. Just a little bit more about the timeline of an offshore wind project. This is unique to the US market, where it takes about, you can see the site assessment and surveys in green there. It says that it takes about 5 years. We've managed to do that in about 3. But it's a lot of work, and it's a significant investment for developers to spend a lot of time and money up front in order to get your permit to be able to construct a project. So probably, you know, maybe 80–90% of the geoscience effort that goes into an offshore wind project happens in that green phase. But the rest of it, you know, once you've laid your infrastructure, there's as-built surveys, there's depth of burial, there's monitoring for scour over the years. And at the very end, we want to make sure that, you know, when we decommission these things, that we're returning the seabed to its original condition. So you start with the baseline and you end with the confirmation of that baseline, maybe 40 years later or 60 years later, if you can find a way to extend the life of these projects, which is something that is definitely being worked. So just to talk a little bit about the scale of these things, you can see right in the middle off of the coast of New Jersey, there's a green, kind of a lighter green. That's an Atlantic Shores lease area. That lease area is 83,000 acres. It's a kind of a large number. We have surveyed that entire lease area with 30-meter line spacing. And we have collected over 2,000 geotechnical investigation points in there of varying types, fiber cores, grab samples, SPY PV, sediment profile imaging, plan views, of course, seabed CPTs, downhole CPTs with the drill rig, and then geotechnical boreholes. So combination of all of those things. And that's just one lease area, right? So it's one thing that I think is really amazing and unique about offshore wind is most developers are very happy to share a lot of that information. Maybe not every bit of it, but there's just so much data that's being acquired that has so many purposes that it's a really, really exciting time. Multiply that by all the projects that are happening. I realize now that this is actually an older map. It doesn't show the 6 new leases that were sold in 2022. And this doesn't include also the lease is in the Gulf of Mexico, the lease is off of California, and the one's off of. So it's a exciting time in offshore wind. And like I said, the best part of an offshore wind project is the geoscience. We get to have the most fun. That's really all I wanted to run through on the slides. Love to open it up to questions. I didn't know like your specific interest level, so I didn't want to go too deep into any one technical bit, but I'm also happy to do that. So.
Sorry, I have multiple questions now.
Please.
Okay, so first off, how are you guys, or I guess, so there's not very many actual wind farms that have been installed, correct?
Mm-hmm.
So what, I guess, are your plans for looking at things like scour and erosion around these environments?
So that's a big topic.
Yeah.
So I don't remember who it was earlier was asking me about models, and I was kind of laughing to myself. So to answer the question about what kind of scour would you anticipate to have over the lifetime of your project? Say you're installing these steel things, you're going to have scour. What's that going to be based on? Well, it's going to be based on the geometry of the thing, right? It's going to be based on the dynamics of the seabed, so the mobility, like the global mobility, which is the big sand waves that are moving slowly over time that you can't really even actually measure necessarily, and with time series maybe, but it's going to be a factor of the currents. And it's going to vary, like if you're a wind project, say your turbines are installed in 30 meters of water, but your cable goes all the way to shore. So you're transecting, you're crossing that whole range of environments. So how do we go about it? Well, as we're doing the design, we collect the mid-ocean LiDAR data. So we're collecting a bunch of data. We're using existing data. We're using existing models for the whole mid-ocean regime. We're building our ground model for the seabed. Where all of those though are models, and all of those are based on what we can measure now, right? The nowcast. What's been measured in the past, and that gets into a tricky one because you think of things like, well, say in 1960, we were using lead lines. Say, and now I'm gonna get this wrong, and so don't judge me.
We had echo centers by then.
Okay. So in 1940, we were using lead lines. In 1960, we had echo sounders. In 2000s, we had multi-beams, and now we have SAS or whatever else we're doing, right? When you take those data sets and you try to line them up in this time series,
It doesn't work very well.
you can make it tell you whatever you want. And same goes for the mid-ocean models. And so when you're answering a question about scour, you're combining multiple models that have so much uncertainty. So what do? Well, generally you over-design, right? But also, you learn from experience. So there are a number of projects that have been constructed in Europe. In some places, like in the North Sea, where they have major sediment mobility issues. So, there is some empirical information there. It's a fascinating one, so.
Will you be doing monitoring surveys continuously after you commission the area?
There will be, yeah, for sure. I mean, there will be at least, annual surveys. But there are some techniques where you can, at least for cable burial, you can install sensors along the cable that help you monitor real time. But for sure, for the life of the project, there will be monitoring. And so, some of the exciting things like, the XL Drix system out of here is going to be those kinds of tools, those uncrewed surface vessels and the autonomous underwater vehicles are going to be really instrumental to doing this monitoring.
So what Julie said is actually not quite correct. There's lots of offshore wind farms in Europe.
But not in the
In the
US.
US, there's, well, there's the new wind farm over Martha's Vineyard, but before that, there were just seven turbines in Rhode Island, Virginia. But I'm not a geotechnical person, but in Europe, I believe that people were surprised what kind of scouring they actually found after 10 years of operation. And so I think there's been quite a bit of learning going on in terms of what you should and shouldn't do. And maybe it's not fully consistent with what they initially thought you should and shouldn't. So
Well, yeah, well, because I know like you said, there is all the offshore wind that's been developed in like the North Sea, but I'm just thinking like those are very different, like soil, specifically from like the geotech point of view, that's like very different than what I would expect to see like on offshore US. So it's just interesting to think about like, it's not, I know, it's interesting to think about like, what are we gonna do about that?
Well, it's one of those opportunities for all of us for the rest of our careers. Yeah.
I actually have a question.
Yeah.
So when you look at what's being done on the eastern seaboard, a lot of the depths are actually shallow enough that you could go with monopiles just from the depth, but then people choose to go with jacketed foundations. What are the geotechnical drivers behind this? When do you go for one versus the other?
Yeah, it's a great question. So there are geotechnical drivers that could be the reason. There are also other drivers that could be the reason. So I'll tackle the geotechnical ones first. Monopiles, I guess, are the most understood. They've been used the most and the most common. So as far as getting a monopile design certified, there's a pretty clear path. They're pretty useful in most soil types, unless you have a condition where you're not able to drive it for some reason, if you have the conditions. Or if you have glauconite. I said the G word, I had to. So the glauconite condition,
Inside joke, I don't.
well,
It's like this awful soil, basically.
it's poop. I'm just gonna say it, but it's like factually it is. But it's a kind of sand clay particle that acts as a sand as you are if you're driving a pile through it, it acts as a sand. So it has a high friction and it appears to have a high capacity, bearing capacity until you push the pile through it, and then it breaks the structure of those particles apart and it acts as a clay. And so it's very difficult to install. And once you've installed it, you don't get the capacity out of a sand. So that is, in fact, probably the main driver for a recent project in the US, somewhere in the vicinity of up here, this yellow one, approximately, to have changed recently from planning to use monopiles to looking at jackets. There's a lot of other reasons though. A lot of it has to do with where is the steel, where are the components for your project being fabricated? How can you install them? Where are the resources coming from for installation? A lot of the driver for the way projects are built off of the East Coast of the US has to do with local content and bringing economic value to the local communities who are, in the vicinity of where these projects are being built. So there's a lot that goes into it.
There's a couple of questions.
Great.
For the people.
Yeah, I can read them out too if you don't wanna.
Yeah, please.
Okay, so we have a couple online questions. The first one is about biodiversity. So essentially asking, are these offshore wind farm structures going to disturb the biodiversity within the catchment area? Maybe could you just comment on your studies of that?
Yeah, for sure. So it's a complicated question. I think it's evaluated through the NEPA process. Anytime you're installing a structure in the seabed, it's going to have an impact on the seabed. but I think the unique thing about offshore wind is the volume of data that is collected to understand the environment. So I think we're learning more than we ever knew about the environment as part of this pre-work. You know, I think it depends where you are, right? It depends on what is the seabed, what's the benthic community in that area, what the impacts will be. In some cases, it's a negative impact. In some cases, it's a positive impact. You know, you look at like, what is an artificial reef? Artificial reef, you know, used to attract fish to the area is a structure that you put in the water. Structures in the water. So from that perspective, there's a positive impact potentially, depending on what your use of the ocean or what your interest is. So it's a complicated question, but it's all part of the, you know, kind of the holistic view that is taken when assessing a project.
And then we have one more online question. Thank you for your enlightening presentation. Could you kindly enumerate on the various data sets that go into building your ground models? And secondly, what are the considerations for selecting wind farm sites?
Yes. Well, so let's start with the selecting sites. So site selection is actually done by the government. It's done by BOEM, the Bureau of Ocean Energy Management. And all kinds of factors go into it. They review who are the users of the area, where is the most potential, where is it potentially constructible, where is an area that is close enough to a populated area that this resource makes a lot of sense, because electrons, they aren't happy the longer you make them move, they lose their electron ability. I'm clearly an electrical engineer. And that's, ampacity is impacted by the geotechnical conditions, the temperature, the depth of burial of the cable, all kinds of things. So the project has to be feasible. And so all of those things are factored into where are the leases. So then the leases, they're auctioned off by the government. Developers invest in those leases and go from there. The tools used to build the ground model, so kind of generically across the board for most projects, but the tools are driven by meeting a set of requirements, and the requirements are depth of penetration, coverage, resolution of data sets, and are you able to answer questions about constructability or geohazards as part of your project. Those guidelines, they also come from BOEM, and how you go about meeting those requirements is up to the developer. However, the requirements basically drive most of us to do it the same way, give or take. It includes ultra high resolution seismic, like I mentioned, typically with the Sparker sound source, coupled with sometimes single channel seismic for cable routes. And that's driven by getting enough depth of penetration, because you not only have to image to the depth of burial for the cable, but that plus 10 meters. And the same is true for foundations, so depth of foundation plus 10 meters. For the cable routes, and then for shallow marine archaeology, it's using an INOMAR, typically subatom profiler. And then I think I already talked about the multi-beam echo sounder, single beam, transverse gradiometer, which is a pair of magnetometers used to identify ferrous objects. A lot of the highest resolution requirements are actually driven by marine archaeology and identifying shipwrecks, paleo channels, as well as unexploded ordnance, which we didn't really talk about too much today, but that's a risk that we do have on the US coast, even though it's not as much as it is in Europe. That was a long answer. I'm sorry, you had your hand up for so long.
Is there any examples of where foundations have failed And if so, was that a geotech thing, an installation problem? And if not, are we over designing them?
I probably shouldn't have said that earlier, over designing, although that's a personal opinion. I mean, human nature, I think we generally over design pretty much everything because we build in conservatism into the assumptions. Those build on top of each other, and then on top of that, we usually put in an engineering factor of safety. Have they failed? I mean, I don't know all of them, but the gentleman back here, the one he was mentioning, there was a very shallow water monopile that was installed. It was like in less than 10 meters of water, maybe 5 meters of water, and they had massive scour. So over half of the foundation was scoured. Even in that case, it did fail in that it maybe had half a degree of tilt, which is too much for a turbine to work. It has to be plumb. So it failed, yes, but that was the failure. And as far as I'm aware, that's the failure that's happened for a foundation. We talk about cables. There have been more things that have happened with cables, where they make landfall. If you HDD them, if you horizontally directionally drill them, and they are 40 feet below the beach in that transition zone area, probably pretty good. But if you surface lay it, it's a pretty violent environment, and things can happen to cables, even or if they're trenched. And then the other big one is we've seen some of the North Sea projects where the cables, where they come into the foundation, they've placed scour protection around that area to prevent the scour, to protect the foundation, but the cables were actually abrading on the scour protection. So a lot of things to factor in. You're in front.
Yeah, so obviously these are federal leases, right? And then they're for a public utility, but you're a private corporation. I'm just trying to understand how that works. And then is the data set considered proprietary in the end of the map itself? Or is that being provided for research or to public?
Yeah. Yes, they're federal leases, managed by BOEM. But the developers are private developers. They're, the end users, in fact, you bring up a really good point that I didn't talk about. Just because a developer has a lease doesn't mean that they have a power purchase agreement. And that power purchase agreement is the utility onshore is agreeing to receive the power that you're going to generate. And so just because a developer has a lease doesn't mean that they have that next step. It's a two-part process in the US. In the Netherlands, it's not. In the Netherlands, if you buy a lease, the permitting, the power purchase agreement is all done, and all you have to do is build it and operate it. The data itself, the geoscience data, it's all part of the NEPA process. And so all of that information, it does get submitted to BOEM. And once it's gone through its review process, it becomes public, with the exception of some of the data is sensitive, particularly around marine archaeology and shipwrecks.
Can I ask a follow-up? So someone online had a similar question. Basically, any advice on how to gain access to those data sets that are publicly available?
Ask us. Where I sit in Atlantic Shores, I mean, I'm also in some other groups. I like to share the data. Anything that we can share, we're very happy to. It usually just becomes a little bit more difficult when you talk about how big these data sets are, and the actual mechanics of moving big data around. It sounds easier than it actually is, but generally we're happy to share.
It's to Julia and Mike. I think we're done.
So is Atlantic Shores plan, or have you, or are you planning to run any pilot programs to test out new survey technology and eventually incorporate it into your either current or future survey plans?
Nothing specifically groundbreakingly or shatteringly new. We had a pretty aggressive timeline and really needed to get a lot of information done. I think the opportunities come after that initial push to get permit applications in and to get that baseline information. I think there's opportunities over the lifetime. I think a real, huge space is in the remotely operated systems of all kinds. There's some challenges with those, right? The uncrewed surface vessels, line of sight issues, permitting issues as far as if you're a developer, you have to have a National Marine Fisheries issued incidental harassment authorization to operate an acoustic system that operates at a frequency lower than 180 decibels, kilohertz. How do you do that with an uncrewed surface vessel? So there's a bunch of challenges, but absolutely, I mean, developers are looking at differently innovating, and I personally am. It's one of my passions for sure.
I just had a quick one. Do you use multi-beam backscatter in the process, or how does it compare against the side scan in that process, I guess?
Yep. We do use it for sure. It's a critical piece in doing the benthic habitat. Understanding the hardness, the relative hardness of the seabed, and being able to differentiate between muds and sands, because that's a big thing when you're looking at the tiny little critters and where they like to hang out. So for sure, we use it for that. We use it for other purposes. I'm blanking on specifically what else, but definitely.
Andy?
Why do you do 300% multi-beam?
Why?
Why not 150 or something like that? That's a lot.
A lot. We are driven to do 30-meter line spacing because of transverse gradiometer.
Okay, so you're doing the multi-beam at the same time.
Why not?
Okay.
So, but there's a benefit, right? There's side benefits. So then you get multiple overlapping data sets and you could do things with that. So say it's been a week since you've come, say you're doing a racetrack and there's been time, and maybe there's been a storm between when you did this swath and then when you did this one right next to it, you end up with overlapping data sets from before and after that storm event. So there's benefit that comes out of it, but it's just a byproduct of the other sensors.
Okay, I think that's all.